All right, welcome everybody. So I'm pleased to welcome our speaker today. It's Matt Zaremsky from the University at Albany, as he told me it's called now. And he's going to tell us something about Houghton-like groups from self-similar groups.
Thank you. And actually, I'm glad that you accidentally said self-similar right there. It says shift-similar,
oh, okay.
But this emphasizes the point of it. Yeah, they're similar to self. This is the downside of having named it this, is that actually I keep accidentally saying the wrong thing myself. But yeah, I'm going to talk about something we invented called shift-similar groups that are kind of similar to self-similar groups, but in a more Houghton group-like world. So let me begin by saying all of this stuff is joint with Brendan Mallory. He is a grad student at Tufts, and we put this on archive. I think it was just this month. Yeah. So let me kind of give you a general idea of what's going on before I really get into it. And by the way, I won't actually define shift similar until at least past the halfway point, and even a bit more than that. So it's going to be a little bit before I actually define the thing in the title, shift similar, this new thing we came up with. But there's a reason for that. And here's a picture of the reason. So here's a picture of Thompson world, and here's Houghton world. Houghton. So here is a circle representing Higman-Thompson groups. Whoops. Higman-Thompson groups, which are certain groups of self-homeomorphisms of Cantor space, essentially, various versions of Cantor space. And then here's something called self-similar groups that I know some people in the audience know a lot about self-similar groups. And they kind of, this is all still in the Thompson world, and they kind of merge together in a certain way to create something called, I need a bigger circle for all these letters coming up here, called Rover Nekrashevich. I can type Nekrashevich pretty fast at this point, but handwriting it, let me see. Nekrashevich. Yeah, I've really built up the muscle memory on how to type it, but I think that's right. Rover Nekrashevich groups. Okay, so that's the picture of what's happening in Thompson world. And for the first part of the talk, I'm going to spend the first part of the talk explaining this stuff, and then I'll talk about the analog over here in Houghton world. So here goes Houghton groups. And then here's this new thing, shift similar groups. And then they turn out to actually be kind of just interesting in their own right. But same with self-similar groups for that matter. But also one reason they're interesting is that they get mashed up with Houghton groups to form, a new thing. Houghton-like groups, we're calling them Houghton-like groups. All right, so that's like the general game plan. And let me then also, before I start defining anything or talking about anything for real, let me just list a couple motivating facts about self-similar groups. And then I'll, not that I've told you what shift-similar groups are at all, but then I'm gonna tell you some things we proved about them that are interesting in contrast with these facts about self-similar groups. So first of all, these are all residually finite. And so in particular, not every group can embed into a self-similar group. If you have a non-residually finite group, you're just never going to be able to embed it into any self-similar group. The other interesting fact here is that there are only countably many finitely generated self-similar groups. Self-similar groups, which, okay, I mean, that can either be viewed as a good thing or a bad thing, I guess, I don't know. Facts about self-similar groups. Here are some facts about shift-similar groups. Shift-similar groups. So first of all, it's gonna turn out that every finitely generated group embeds into a shift-similar group, into a shift-similar group. And then I guess immediate consequences of that is that there are uncountably many of them. Uncountably many finitely generated shift-similar groups. So this is in contrast to self-similar. And then like one more little fact I want to mention just because it's kind of interesting. And also now I will at least sort of give you a sense of at least where shift-similar groups are like living for any infinite shift-similar G subgroup of sim n. So this is the kind of ambient world in which these shift-similar groups are going to arise from. They're subgroups of the group of all permutations on a countably infinite set. Of course, every countable group embeds into sim n, but it's still an interesting place to hunt around for groups. I don't know. Anyway, for any infinite shift-similar group G viewed as a subgroup of sim n, we have that it contains the entire finitely supported subgroup of permutations. Sim fin, we call this sim sub fin. Every finitely supported permutation is going to live in every shift-similar group. So there's a bit of structure happening here, and maybe this gives you kind of a little bit of a picture of what sorts of groups we're talking about with this. Yeah. Okay, so this is the very general little cartoon. And now I want to work through Thompson world. Part 1, that was part 0, I guess. Part 1, Thompson world. Thompson world. First 1A, Higman-Thompson groups. Higman-Thompson groups. Let me just go ahead and define these in a way that'll kind of end up segueing into the other stuff. Consider D-Airy Cantor space. So this is, you take the alphabet of letters 1 through D, and you look at all infinite strings of letters from that alphabet. This is D-Airy Cantor space. Cantor space. Also some notation, let 1 through D with an upper star here be the set of all finite words, set of all finite words in that alphabet. The Cantor space is the infinite words, and then this thing with the star is the finite words, set of all finite words. And now I'm going to define certain subspaces of CD for each finite word W. Let CDW be the set of all elements of the Cantor set that start with a W. So I'm going to write W kappa. I like using kappa for an element of CD. Let this be the cone on W. So if W is like, I don't know, 1, 1, 1, then this just means the set of all infinite strings in 1 through D that start out 1, 1, 1, and then you can do whatever you want. That's the cone. Can I define, oh no, one more little observation before I can define the Higman-Thompson groups. For any cone, for any CDW, we have a canonical homeomorphism. From, now which way do I want to? I want to go from CD to CDW, given by just sticking a W at the front. Yeah, so all the cones are homeomorphic to the original DRE Cantor set. In particular, CD contains a whole ton of copies of itself. That's like a recurring theme here. CD contains all sorts of copies of itself. Yeah, all right, now I can define. The Higman-Thompson group, VD, is the group of all self-homeomorphic, let me write VD subgroup of homeo CD is the group of all elements F built in the following way, built as follows. So here's how you construct an element of VD. Step 1, partition CD into cones, into finitely many cones, CDW1 plus CDWN plus for some n, finitely many cones. Do it again. 2 ways. Got a sort of a domain partition and a range partition. Do it again. CDW1 minus CDWN minus, same number, same n, same number of cones. And then step 3, okay, so now the point of this is we're building a homeomorphism from CD to itself. So do that, build F from CD to CD by sending each domain cone CDWI plus, I think plus was the domain cones. That's supposed to be a plus. To some CDWJ minus. And do it via these canonical homeomorphisms. So I guess you have to do, first you do the inverse of the one for WI plus, and then you do the one for WJ minus. Yeah, because I said, so the canonical homeomorphism adds a prefix. So here what it's saying is that you start with the cone defined using prefix WI plus, and then H inverse removes that prefix, and then H, the other H, adds the new prefix. So you do a prefix replacement. Prefix replacement. And it's an exercise to check that this really is a subgroup of homeo CD. You have to do a little bit of work to see that this is that a composition of such things can again be realized in the same way. But let me draw a little picture actually. So if you think of the Cantor set, if you think of the DRE Cantor set as the boundary of the infinite rooted regular DRE tree, then these cones, then the name starts making a little more sense. the cones are kind of like this. Here's the cone on 1, and then this is 2, 1, and this is 2, 2. And now an element, oh, for example, I don't know, I can do whatever I want really. I'll use ABC to indicate the permutation. Notice that you send each whatever sub I to a whatever sub J, like you can change the order. So here in my permutation, maybe ABC turns into BAC. And the cone, so this would mean that the cone with prefix 1 becomes the cone with prefix, what is that, 1, 2. The cone with prefix 2, 1 maps to the cone with prefix 1, 1. And the cone with prefix 2, 2 maps to the cone with prefix 2, yeah. Okay, so this is a thing you can do. This is a certain group of homeomorphisms of the Cantor set, D-ary Cantor set. When D is 2, you get the famous Thompson's group V. So this is a whole family of generalizations of that. And yeah, good. Okay, so I have successfully defined the Higman-Thompson groups, and now I'll define self-similar groups. And for the purposes of this talk, self-similar groups are these things that exist to be mashed up with Higman-Thompson groups. Hang on, I have to let my cat through the door. Okay. It's almost time for the cat to eat. All right, self-similar groups. Let TD be the infinite, rooted, regular, D-ary tree. I feel like at least one of those words didn't need to be written, but so the vertex set of TD, this is supposed to be a T. I think it looks a little weird, TD. So the vertex set of TD is exactly that set of finite words in the alphabet 1 through D that I was talking about earlier. You have a vertex for each one of those, and CD is the boundary of the tree. And then the adjacency is just given by adding a single new letter at the end. A vertex W has, call them children. Children W1, W2, up to WD. So those are the vertices immediately below W. Okay, and now, all right, so now I'm gonna gradually define self-similar groups, and I'm gonna do it in a way that will mirror how I eventually define shift-similar groups. So this is maybe not, it's mostly the way that you might be used to seeing self-similar, but maybe with slight differences. First of all, for each I between 1 and D, let TDI be the subtree of TD with vertex set. So now instead of looking at all finite words, I want just the ones that start with I. Vertex set I, W, such that W is a finite word. You have one of these for each I. So this is the tree based at, or rooted at, I don't know, based at the vertex I. Here's a picture. I'll use 3. Whoops, what did I do? Here's T3-1, T3-2, T3-3. And of course, each of these things is just isomorphic to the original tree. Each TDI is isomorphic to TD via, I'll call it delta I, from TD to TDI. This is like a graph isomorphism, I guess is what I mean by isomorphism. And on the level of vertices, yeah, I'll just write this here. W goes to IW. That's what it does to the vertices. Yep. Okay, so all of these subtrees are isomorphic to the original tree. Just like how in 10 minutes ago, I was saying CD contains a whole bunch of copies of itself. And CD is like the boundary of this tree. So now I'm just talking about the tree itself, and it also contains a bunch of copies of itself. This regular tree contains a bunch of copies of itself. So we can use this to decompose the group of automorphisms of the tree. Aut TD, by which I mean graph automorphisms. For aut TD, the automorphism group, we have a map rho from aut TD to the symmetric group SD by looking at what a given automorphism does to the top level, because it has to fix the root. The root, any automorphism of this tree has to fix the root because it's the only vertex with degree D. All the other vertices have degree D+1. So it's got to fix the root. And more generally, it has to stabilize every level. So now looking at what it does to the first level, by looking at the action on the first level, we get a map to SD. Action on level 1. And the kernel is pretty clearly, actually, can probably just say literally equal to, I'll write isomorphic just to be safe. Aut TD1, direct product up to aut TDD. Yeah, the kernel of rho is just going to be all the guys that don't do anything at the top level, but then you can do whatever you want to each of these subtrees. And since I said each of those subtrees is isomorphic to TD, we get that the kernel of rho is isomorphic to a direct product of D many copies of aut TD. So we get a decomposition and this map splits. I guess that's pretty obvious too. So we get a decomposition of aut TD as SD semi-direct itself to the D. Or you could write this as a wreath product. Okay, and now I'm gonna write, it's a lot of notation. Now I'm gonna write the following for this map. I'm gonna say that if you take an automorphism of TD and you view it as first, like what does it do to that top level, rho of G, and then what does it do to each of the D many subtrees, I'm just gonna call those things phi1 of G through phi D of G. So phi1 of G is like, look at what G is doing, restricted to T1, restricted to TD1, it maps TD1 to some other TDI. And what does it do? Well, it acts like a tree automorphism. That's what I'm calling phi1 of G. So if you want a little formula here, phi I of G is delta inverse sub row of G applied to I compose G restricted to TDI. So that's, you're looking at what does G do just to that subtree. And then you had to begin that with delta I. So phi I of G is an automorphism of the original tree, but you obtain it by first taking this canonical isomorphism to the subtree and then looking at what G does to that. Now you end up with some other subtree, do the reverse isomorphism to get back to the original tree. Whew. So there you go. And now I can finally define self-similar. A subgroup of aught TD is self-similar if for all G in G and for all I between 1 and D, phi I of G, not only is it again an element of aught TD, but it's even an element of G. So this is a restriction. Yeah, so it's okay. So self-similar means that you're an automorphism of the tree, but now if you like restrict and just look at what you do to one of these subtrees, then upon viewing that subtree as a copy of the original tree with the restricted action of G, that still corresponds to an element of G. So it's like you, hang on, so yell at my daughter for a second. Stop, go away. So, okay, so good. So that's what self-similar means. The most famous example is, what time is it? Yeah, okay, I can. The most famous example is the Grigorchuk group. Grigorchuk group. I'll call it Grig, living in aught T2. It has 4 generators, A, B, C, D, and the action can be recursively defined. The action on the tree can be recursively defined. Via, so if we focus on the top level and then also look at what it does to the 2 subtrees underneath, A, B, C, D, map to, okay, so A just simply permutes them. It's just the transposition. B doesn't, I better double check this. B, yeah, none of the rest of them flip it, I think. B doesn't flip it at all, and then it propagates as AC. So B flips the first subtree and then acts like C on the second subtree. What does C do? Well, it flips the first subtree and acts like D on the second one. What does D do? It doesn't do anything to the first guy, and it acts like B on the second guy. This is a recursive definition, and you can kind of start drawing pictures and figure out what these actually look like. But the point is that in all of these cases, at least here for the generators and hence for any element, when you look at what it does to the subtree, it's yet again another element of this group. The entries in the tuples, the entries in the tuples are again not only automorphisms of the tree, but they're even elements of the Grigorchuk group. Okay. And then let me reiterate these facts. So actually, now that they're defined, it's not too hard to see that self-similar groups are residually finite because they're kind of just like constructed by looking at these maps to finite groups. Self-similar implies residually finite. And I don't know, I guess this is less obvious, but there exist countably many, yeah, I already said this, but there exist countably many finitely generated self-similar groups. I guess that's sort of like, given a number of generators, everything is completely determined by which words in the generators you use as these states. I didn't call them states, but the restrictions. And I guess, yeah, there's just kind of like countably many data happening here.
Are you sure, Matt, that that's true if you don't require them to be automaton groups? If it's automaton groups, it's clear there's countably many automata, but the sections don't have to be, simple product. They don't have to actually, be other generators or be finite state. That you could have non-finite state automorphisms, which have infinitely many sections and generate a self-similar group. Yeah. It's less so clear to me that those are countably many. If it's an automaton, if they're finite state, that's clear.
Yeah.
Whether they're not obvious. Finite state.
So it's funny, right? Okay, so this was not clear to me whether, and I couldn't find it. I couldn't find anything about it in Nekrashevich's book. So then I emailed Nekrashevich and asked him, and then after I'd emailed him, then I found the spot in the book. And yeah, there are only countably many finitely generated self-similar groups. And
okay, it doesn't care whether they're finite state or not.
It doesn't matter. And he poses, nobody knows whether the same is true with finitely generated replaced by countable. Are there only countably many countable self-similar groups? He said he doesn't know. I'm sure he hasn't thought about it much either, but yeah, I thought this was not going to be true. So I was hunting around for some reason for some construction of uncountably many. And then I stumbled on that actually, no, there's actually only countably many. Yeah, it was a little surprising, but right, if each generator, if each state of a generator is again a generator, then it's obvious. But yes. Okay, perfect. And now let me very quickly define Rover-Nekrashevich groups, and that'll complete this whole like picture of Thomson world. Section 1C, Rover-Nekrashevich groups. And this will simply be that I take the definition of the Higman-Thomson groups and then I toss in some self-similar groups toss in a self-similar group. For G, a subgroup of aught TD, self-similar, the Rover-Nekrashevich group, the Rover-Nekker group, VDG is the subgroup of homeo-CD. The Rover-Nekrashevich group VDG is the subgroup of all elements constructed by the following procedure. Constructed via, all right. So this will be familiar. You partition CD into cones, finitely many cones, CD. What did I say? W1 plus up to CDWN plus. Do it again. CDW1 minus, CDWN minus, same number, just like before. And now I will build F from CD to itself by sending each CDWI plus to some CDWJ minus via, and now we have to remember these canonical homeomorphisms, but I'm going to squeeze in also an element of the self-similar group right there. Something needs, in my notes, there's a typo because neither of these has an inverse on them. Which one is supposed to be inverse? It's the right one.
One on the right.
Yes. Okay. Yeah. Okay. So it's basically saying you take the cone with prefix WI plus, remove that prefix. Now you just have CD. that's the boundary of this tree TD. So you can act on it with GI from your self-similar group. And then after you've done that, then you put the new prefix on. Now you put WJ minus on. I didn't really emphasize that, right? So the self-similar groups live in aught TD, but then they embed into homeo CD because that's the boundary and they act faithfully. Probably should have said that earlier. Anyway, okay. Yeah, so this is the Rover-Nekrashevich groups. These things are important. They tend to be simple or at least kind of close to simple. So they're a good source of examples of simple groups. Rachel Skipper, Stefan Witzel, and I used these things to find the first examples of simple groups of type Fn-1, but not Fn, through the finiteness properties, type Fn. Yeah, these are good groups. So, okay, that completes the picture of Thomson world, and now we move into Houghton world. Oh, let me just out loud quickly say, so the reason that we needed G to be self-similar here in this definition is to get this to really be a group. In order for this thing here to be closed under conjugation, you have to essentially be able to like refine the partition into deeper cones. And when you do that, you need the restrictions of the elements G give you yet again elements of big G. That's really the reason. Yeah. Oh, and then the other little thing I wrote here. So when you use the Grigorchuk group, you get what is now called Rover's group. Rover considered that, and then Nekrashevich generalized it to all G. That's where the name comes from, Rover-Nekrashevich. All right, now I am actually ready for Houghton world. Houghton. Oops. Oh, come back. Houghton world. All right, so Houghton's groups. Let me define Houghton's groups. Houghton groups. I'm gonna always write box N for 1 through N and consider the following kind of analog of the tree TD. Instead of a tree, I'm gonna now be looking at the set box N cross the naturals. So this is like you take, here I'll take 3 copies of the naturals laid out like that. And now if you've seen Houghton's groups before, so I can just out loud, I guess, say Houghton's group HN is the group of all self-bijections of this set that if you go out far enough, it just looks like translation of these rays. But I'm gonna define it a little bit unconventionally. First, I'm gonna set up the analog of cones. So if we're kind of thinking of this as instead of like the tree or the Cantor space, now we're looking at this thing. Here's the analog of cones. For a finite subset of box N cross N, let or define the kth, call it quasi-ray, QKM, to be that you take, so QKM is you take the kth copy of N and then you remove any points that happen to be in that finite set M. So ultimately it's just a copy of the naturals minus finitely many points. Yeah, I guess a ray, the ray is the whole copy of the naturals. Quasi-ray is like you're missing finitely many points. Good. And note that each, so just like in the Cantor set, each cone was canonically homeomorphic to the original Cantor set. Note that each QKM is canonically, there's not really a topology happening now, so it's just canonically bijective with N via beta for bijection. Beta KM goes from the naturals to the quasi-ray, and you just send I to, there's not really another way to say this, the ith element. It's so canonical that you can just sort of say that.
Doesn't your M have to be a little restrictive?
My N?
My M. M as in Matt.
Oh,
like solid.
No.
Points scattered around.
No, I mean, so like if
the bijection can squash things together.
Yeah.
Okay, fine.
So I guess so ith element is ambiguous.
It's the unique order preserving one, right?
Yeah. It's the ith element, which may be the I plus first element of the original thing before you remove the finitely many points. Yeah.
It's just a sub-well-ordered set that looks exactly like the naturals.
Yeah. So continuing this theme, right? The naturals contain a whole lot of copies of itself. The set of natural numbers contains a whole lot of copies of itself. Yeah. Continuing the theme of things containing copies of themselves. In fact, any infinite set is canonically bijective. But here I want to look at what would be the word co-finite, I guess. Remove finitely many points. Yeah. Okay, so now I can define the nth Houghton group. Hn is the group of elements of sim box n cross n built in the following way. Built as follows. Step 1, partition box n cross n into, first of all, a finite set M plus and its corresponding quasi-rays. Q1 M plus up to Qn, n M plus. Do it again with some finite M minus with the same cardinality. And now I'm going to build the self-bijection by sending, first of all, sending M plus to M minus via some bijection, sigma. Just call it sigma. Do whatever you want on those finite subsets. And for each k, send QKM plus to QKM minus via the thing built out of the canonical bijections. So it should be beta KM minus compose beta KM plus with an inverse. This time I did remember the inverse. Like that. So instead of a prefix replacement on cones in the Cantor set, now it's like you're sort of taking the quasi-ray. Well, first you do whatever you want on the finite set, and then you take the quasi-ray, view it as n canonically, and then undo the viewing of the other quasi-ray as n via that canonical bijection. Or maybe the first one's really the undoing, but yeah. Both quasi-rays are canonically bijective with n, so they're bijective with each other. You can map the one to the other like this. Very analogously to the definition of the Higman-Thompson groups. And then maybe just out loud, I'll reiterate that the usual definition of the Houghton groups is this thing about all of the self-bijections that are eventually translations, but that gives you the same thing, because if you go out far enough, since I was only ever removing finite subsets, all of my quasi-rays eventually are contiguous is maybe the right word. Eventually in your quasi-ray, it just looks like I plus 1, I plus 2, I plus 3, whatever. And then in the other one, if it was missing a different number of finite points at the beginning, then it's like shifted differently. So there is this translation happening out far out. and then you can do whatever you want in the finite zone. So yeah, it's the same thing. This is like an unusual way of viewing Houghton's groups, but one that makes it very analogous to Thompson groups, which I like. All right, now I will finally define.
Sorry, just a quick question. How does the sigma bijection come in? Because in your composition, it doesn't seem to come in.
Oh, no, okay, right. So when you compose, you have partition into an M plus and its quasi-rays. Here's M minus and its quasi-rays. And then in your other element, call it N plus and N minus. And in order to actually compose these, you have to first kind of expand the finite sets so that the domain one of the second one equals the range one of the first one. Wait, yes. Yeah, the range one for the first one has to equal the domain one for the second one. And when you puff them up like this,
it's better to have, when you compose them, you have to use it to figure out how to make them line up. And
yeah.
Okay, I see.
Yeah, you have to cut off pieces of the quasi-rays and add them to the M sets in order to be allowed to compose two things directly. Although, I mean, I don't know, in some, and then even if you did just have, even if it was already laid out like that, the sigmas matter, right? I mean, the bijections between the finite sets matter because they compose as bijections and you get an overall bijection. Yeah. I think the thing I was talking about will be more important in a second, actually. But anyway, okay, let me define shift similar groups now. So again, I'm gonna exploit how if you take n and then you remove finitely many points, or really just one point at the beginning here, then it's like canonically bijective with itself. Let Sj from n to n minus j be the shift. I guess I'll write it out. It's you either get I or I plus 1, depending on what's going on, depending on where you are relative j. And now, since I kind of already set things up earlier in Thompson world, I don't have to really motivate the following too much. Let psi j from sim n to itself be that it sends a permutation G to write it out and then think minus J compose Sj. Okay, so this is saying first you do the J shift, you kind of slide everything up so that there's a gap at the number J, and then you apply G to that, whatever that does. And now the gap is no longer at J, but now it's at G of J. So now do the canonical unshift where you close the gap at G of J. And overall you get a permutation of N that pretty much amounts to taking what G does and then just kind of forgetting what it did to J. So let me draw a picture. You're just like forgetting the Jth arrow. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here's a permutation of N. Let's say that 1 goes to 3, and I'll do a dashed line because this is the one I'm gonna delete in a second. 2 goes to 5. I copied this right out of the paper. 4 goes to 2. 5 goes to 6. 6 goes to 4. So I'm gonna hit this with psi 1. which means that you take all your numbers, you slide them up so that there's a hole at 1. You're not even looking at 1 anymore. You do you do G to whatever's still there, so everything except 1. And then you, come in, cat, and now you have a gap at 3, so just like slide down to fill the gap. And it's sometimes hard to actually draw these pictures, but just because the numbers are changing all over the place, like 1, so 1 goes to 2, and then 2 goes to 5, and then back down to 4. So 1 goes to 4. Let me just copy it out of my notes. 2 goes to 1, 3 goes to 2, 4 goes to 5, 5 goes to 3. Okay. So really what it is if you draw your element using arrows like this, you're just deleting the arrow originating at J. J is 1 in this picture. Yeah. You have some permutation of n, and now you erase one of the arrows and shift all the numbers down to fill the gaps. And I didn't actually define. Okay, so that's what psi j does, and then probably you've figured it out by now, but call G shift similar if for all G in G and for all J in N, psi j of G is again in G. Yeah. So the group is closed under erasing arrows. I guess I should linger here a little bit. This is kind of the key definition. Yeah, you picture the permutation of n using arrows in this way, and then in order for the group to be shift similar, you need that erasing any arrow and shifting things accordingly, you get a new permutation. You need that permutation is also in your group. Once again, exploiting the fact that n is canonically the same as various subsets of itself, just like the tree and the Cantor set and whatnot, and the n cross box n cross n, which is about to come up. Yeah, okay, so that's what shift similar means. And then I can kind of just quickly talk about Houghton-like groups. In fact, let me be very quick about this and just say, yeah, since there's only 7 minutes left, do the same thing to build HN, but now to get HNG, just like in the Rover-Nekrashevich groups, you take the Hickman-Thompson group, and then like as the cones are mapping to the other cones, you mess with them using the self-similar group. And now same thing, but we're gonna mess with the map using the shift-similar group. So where's the key formula here? Now send each quasi-ray Q of Km plus to Q of Km minus via, let me write this from right to left. So first you view the plus quasi-ray, you view it as n, and then you hit that with GK, and now you have n, and then you view n as the minus quasi-ray. Right. Okay, so in the Houghton-like group, it's again that you do whatever you want on a finite piece, and then really far out or whatever, you have to act by eventual translations and also elements of the shift similar group. You can kind of twist any given ray really far out using an element of the shift similar group. And the shift similarity ensures that HNG really is a group, because when you compose two things, you might have to expand.
GK, what is that?
Oh, sorry, for GK in G, where, yep, didn't say it, where G in sim n is the shift similar group that I should have written down at the beginning.
And GK?
You just have one for each K. You just have an element, like a different element for each. Or did I write? Yeah. Like each, there are n many rays, and you can do a different element of G on each one.
Oh, I see.
Yeah. Because maybe I should have written out the whole, because these are now bijections of box n cross n to itself. You have n copies of the naturals. Is shift similar. Yeah, I just kind of wrote G inside the HN, but and in order to ensure that HNG really is a group, just like with Rover-Nekrashevich, you needed G to be self-similar. Now, in order for HNG to be a group, I need G to be shift similar. It's kind of exactly the condition that you need in order to ensure that thing really is a group. Okay, so quickly at the end here, I guess let me just remind you of the main results. Every finitely generated group embeds in a shift similar group. Embeds in a finitely generated, that's kind of, otherwise it's obvious. In a finitely generated shift similar group, and then corollary, there's uncountably many isomorphism classes of finitely generated shift similar groups. And then now that HNGs are around, I can say that a shift similar G, it turns out, yeah, we proved it's amenable if and only if HNG is amenable. So that's, I mean, the Houghton groups themselves are elementary amenable, so maybe this isn't that surprising, but it was a little harder to prove than we expected. And then also things like, this one's pretty surprising. Every infinite shift similar G contains the entire finitely supported group. Yeah, you can, I mean, even if all you do is you start with a single permutation of infinite order and then take the shift similar closure of it. So just like take it and every shift of it, the thing generated by this, you just have to make sure it's closed under products and closed under shifts. You manage to catch the entire, every finite support element. It's kind of surprising. And okay, let me just say, question, here's the biggest question. In my mind, here's the biggest question. So there's uncountably many finitely generated shift similar groups. Find question or problem. Find finitely presented examples. This is hard. So the Houghton groups themselves actually admit shift similar representations. And for H3 and higher, those are all finitely presented. But unless I'm forgetting something, I think that's like it for examples that we're aware of. It's really hard to build examples of finitely presented shift similar groups. And I guess to some extent with self-similar, I know that like free groups are self-similar, but sort of morally speaking, they tend, I think self-similar groups tend to be finitely generated, but not necessarily finitely presented, like Grigorchuk's group. So maybe it's not surprising that it's so hard to find finitely presented examples here too. But that's, I'd say, the biggest problem. And then the other main problem is the definition requires you only have to be closed under like downshifts. And in practice, any of the examples we found kind of miraculously, you're also closed under upshifts. And that seems like it shouldn't be necessary. So question whether that has to happen. But okay, out of time, ended exactly 5 o'clock. Good stopping point. Thank you.
All right, thank you very much for the talk. Okay, so now if there are any questions to the speaker, you're welcome to ask them. So I had a question actually. So regarding what you said at the very end, So about finely presented examples.
Yeah.
So Bartoli has this notion of a finite L presentation where the presentation itself is in, but it has sort of up to a certain kind of algebraic shift or algebraic shifts. You know, there are only finitely many relators, and that ensures that the group embeds into a finely presented group via either a single HN extension or like an HN with finitely many stable letters. I was wondering whether something like that might be sort of possible.
Yeah, that had not occurred to me, but maybe. I guess probably not uniformly, because then
at least at the level of examples. Because Grigorchuk group is like that, right? You know,
right.
Not finitely presented, but it admits a finite L presentation. I guess it was is Igor Ilshonak still here? You know, I don't remember who found it. Igor, are you here?
Yes, I'm here.
So I think it might be your presentation. I don't remember now who found that presentation. You know, which has this.
I sort of thought Grigorchuk himself did.
It's Igor, I think.
Is it?
I thought it might have been Igor Ilshonak who found it, but I do remember that this presentation exists, and it sort of it has this property that if you you get I mean Grigorchuk group, of course, it has many different presentations, but if you use the right one property, and then you get from it this.
Never mind. I was thinking of his torsion-free version, but that's totally different. Grigorchuk himself did that one, but
anyway, that was my comment.
Yeah, maybe something similar works here. Certainly not uniformly, because then you would get a finitely presented group containing every finitely generated group, and that's
no.
That's not good.
Right, because you are also asking here a question about examples.
Yeah. No, that had not occurred to us. That would be interesting. Yeah.
I just have a quick question. I mean, I think one reason why Nekrashevich was interested in these Rover Nekrashevich groups is because they come up naturally inside of his Nekrashevich C-star algebras for self-similar groups. And I'm wondering if there's maybe some natural ring that's sort of like a Nekrashevich algebra, but that somehow replaces Cantor sets with natural numbers or something like that. If there's some sort of general structure where these things would live naturally.
Yeah. I know very little about C-star anything, but but I know, and isn't it also, I want to say that the Nekrashevich group tends to be like isomorphic to the abstract commensurator of the self-similar group. But I guess that's pretty specific to finite index. Everything in that world is all about finite index. I don't know what the analog would be.
I mean, his kind of comes from, there's sort of a groupoid associated to this, and the group is like, it's a topological full group of the groupoid, but I don't know if since there's no topology on the natural numbers, if there's a groupoid, it would not be topological, but still somehow feels like, I mean, because you have these canonical like guys and their inverses, there's somehow an inverse semigroup sitting around there, and then you're kind of building up it's somehow you're looking at locally isomorphic things and then gluing them together, and so it still feels like there should be some topological groupoid or something, some inverse semigroup where you'll see a similar construction, but because it seems to be built up in a very similar way where you have these kind of one-sided isomorphisms and their inverses, and then you're allowing yourself to kind of glue these together, and the shift similarity lets you commute group elements with these one-sided maps in a certain sense to pass them one side of the other, which is what you would want to make the group and the monoid generate like something which has least common multiples or array property or something.
And thinking of topological full, so it sort of feels like the analog, or the reason for the topological there is you care specifically about, open, like Clopin sets, you care about these cones, whereas here you mostly care about n with finitely many points removed. So I don't know if I don't know what topology such things form. But
I kind of feel like probably you would end up completing this to something which is compact, exploiting cofiniteness, because there's a sort of canonical machinery that takes an inverse semigroup, like the one you have up there, and pops out a groupoid and then a group. And my guess is that if you did this with just the Houghton world, with the Houghton part, you'd get the Houghton group, but then your thing would get thrown in, and then you'd have to replace the inverse semigroup with a bigger one, which has your group in it. But I haven't thought about it because I'm just absorbing the definitions. But it looks so similar. I mean, there's these partial one-to-one, partial bijections floating around here that are controlling everything, and then you're gluing them together. So it seems like something like that should happen.
And we didn't even do this, but there in Thompson world, there's also this space. Yeah, there's a groupoid and there's a poset and there's a space that it acts on and reveals stuff. And you can do all that. We didn't do it here because we typically use that for finiteness properties. And here we couldn't even really find any shift similar groups with interesting finiteness properties. So if you don't even have those to plug in to the machine to output, then why do you have it? But I mean, it seems like it should be true that if G is finitely presented, so is HNG, for example. And I think you would use all that machinery, the Houghton analog of all that Thompson-like machinery. But yeah, the paper was already like over 30 pages, so we didn't do that. But if we can come up with more examples of shift similar groups with interesting finiteness properties, then it would become worth doing all that.
Maybe you can find some which are somehow not finitely presented, but still have the homological property or something.
Yeah, that would also be interesting, right? Yeah.
I mean, that would be a strange way to find them since they're normally found different method, but
yeah. Basically anything I ever discover that's homological type FPN, it's gonna also be type FN though. Like I don't know any homological tricks. But yeah.
Okay. Are there any other questions?
I have a maybe stupid question. Are there any, I don't know, some good examples of this shift similar groups? So it's like a mixed group.
So I think the best example is the construction of how to embed an arbitrary finitely generated group into a finitely generated shift similar group. So first take N, chop it into evens and odds, and then there's a copy of Houghton-2. So that's like Z. Mm-hmm. Houghton-2, normally you think of acting on Z. You have the shift, and then you can do anything with finite support. Mm-hmm. So now we're viewing evens and odds. It's kind of this like slide thing and finite support in the middle. And it turns out this is finitely generated. This is Houghton-2 is generated by two elements. You just need the shift and you need a transposition. So then take your arbitrary finitely generated group and realize it, have it act on itself, I guess. Like if it's an infinite, it acts on N. It acts faithfully on N. Stick that just on the odd part. And then together with the slide and all finite support guys. And by construction, this is now shift similar. Oh, yeah. Sorry. Well, you also need the flip. I forgot. Okay. You need to be able to flip even and odd. But by construction, this is shift similar, because now if you do anything, it's hard to, okay. You do anything, erase an arrow, slide down. Let's say that the convention is that every odd number falls down to the even number just below it, and every, oh, you don't need a convention, and every even number falls down to the odd number just below it. So the roles of even and odd are reversed. I'm making this more complicated than it is. After you delete an arrow and slide down, whatever you get now is still in this same group, because you can kind of use a slide to put it, a slide and a flip to put it back where it came from, up to finite support stuff. But you have all the finite support stuff, so that's okay. Yeah.
But okay, that's if this group is okay in a sense good. So can you, for example, write down some kind of presentation for it?
I mean, maybe.
Okay.
If you with this exact construction, you toss it in just on the odds.
I mean, if you define a group just giving to say it's two generators, it doesn't mean that it's it doesn't mean that it's good in a sense. So
yeah.
How to understand it? Okay. Okay, but anyway.
Yeah, I'm even now. I'm for Houghton 2, right? There's 2 generators. I don't actually know maybe an infinite presentation, but off the top of my head, a presentation for H2. You need lots of. I guess it's like a lamplighter probably, where you just you need all the conjugates of the transpositions commute, and you need all of them, something like that. And then you toss in your arbitrary group on the odds. Yeah, that seems like a big mess. I don't know.
Okay.
It's a good project for a grad student. Brendan can do this. Yeah.
Thank you.
All right. Okay. Anything else? Okay. Let us thank Matt for a very interesting talk. Thank you. Now I'll stop the recording. The official portion will be over.